Alright guys, so in the last video we looked at how we can take the concept of completing the square and apply that to standard form of a quadratic function. And when you apply that, we can actually use it to solve this equation for x, even with the a, the b, and the c in it. We can solve it for x, and since x gives us our solutions, what that does is it gives us a formula that we can use to plug in a, b, and c and find the solutions to a quadratic equation without having to factor, without having to complete the square, without having to graph. We just simply plug them into the formula and solve. So by far it is probably the easiest process to finding the solutions, but there's a lot of things that we have to understand first before we do that, which is why this is the last process that we're using to find solutions for a quadratic equation. So here's our formula, negative b plus or minus b squared minus 4ac over 2a. So in this video we're just going to look at a few different examples. We're going to look at one example where we get real solutions, one example where we get imaginary solutions, and how we're going to simplify with that. And then also one example with fractions and how we can handle that and actually make it easier than it may seem at first. So in the first example, we're going to look at 2x squared plus 3x minus 4. Now, before we kind of go any further, just want to identify, a is 2, b is 3, and c is negative 4. And once we establish that, we have everything that we need to plug this into the quadratic formula. So again, that quadratic formula is negative b, so this time it would be negative 3, plus or minus b squared, so 3 squared, minus 4 times a, so that's 2, times c, so that's negative 4, over 2 times a. Alright, and actually I'm going to go ahead and change that. 2 times 2, we'll go ahead and say 4. Alright, so we'll continue this process and start simplifying. I like to begin the simplifying in here. This part of it is called the discriminant. We're going to talk a little bit more about that in detail later, but I like to start in here. Order of operations, this is where we have to start. So we'll do 3 squared, which is 9. So I'm going to say 9. Negative 4 times 2 is negative 8. So negative 4 times negative 2 is negative 8. Times negative 4 is positive 32. So we have 9 plus 32. 9 plus 32 is 41. So I'm actually just going to go ahead and rewrite that under here, the square root of 41. And we have negative 3 plus or minus the square root of 41 over 4. And so from here we're going to continue to simplify this. Alright, so the square root of 41, it's not a perfect square, but it's about 6.4. So we'll say negative 3 plus 6.4 over 4. And then we're also going to need to do negative 3 minus 6.4 over 4. And this will give us our two solutions. So negative 3 plus 6.4 is 3.4. Divided by 4 is 0.85. So we've got 0.85. Oh, that's not an 8. 0.85. There's one of our solutions. And then to get the other solution, we'll do what's here in red. We'll do negative 3 minus 6.4, which is negative 9.4, divided by 4 gives us a negative 2.35, which is our other solution. Now, back over here, just to kind of talk about this for a second, when we don't end up with something, excuse me, under the radical that's a perfect square, you've got a couple options. In this one, there wasn't really any way we could simplify it because 41 is a prime number, and you can't simplify prime numbers under the radical. So I just went ahead and found that approximate decimal, and then we can use that approximate decimal to actually get our approximate answer. So again, it is just approximate. This was 6.40 something. It was a mile-long decimal in the calculator. But our other option would be if this can be simplified. Let's say it was the square root of 50. Well, 25 times 2 is 50, and 25 is a perfect square. So the square root of 50 could be simplified and left in radical form. And then even at the end, you could find the decimal. A lot of times, especially later on when we're going to be graphing things, the decimal is what we're going to want anyways. Graphing in radical form is a little abstract, so the decimal is going to help there. So this is the first example, and again, this is an example where we get two real numbers. In the next example, we're going to get something a little different. So we're going to look at how we're going to simplify that in the next example. All right, so 3x squared plus 5x plus 12. So I'm going to go ahead and plug all of this in. We'll have negative 5 plus or minus the square root of 5 squared. So I'm going to go ahead and say 25 minus 4 times 3 times 12 over 2 times a is 3, so over 6. We've got negative 5 plus or minus 25 minus 4 times 3 times 12 over 6. So we'll go ahead and start simplifying again in here in the discriminant. So I'll do negative 4 times 3 times 12, which is 144. So continuing this, we have negative 5 plus or minus the square root of 25 minus 144 over 6. And 25 minus 144 is negative 119. So negative 5 plus or minus the square root of negative 119 over 6. Now, obviously, we're going to end up with a complex number because we have the square root of a negative number, which is not a real number. So instead of actually simplifying this all the way down, we're not going to worry about getting that decimal because we're graphing in a coordinate plane that doesn't have imaginary numbers, so we wouldn't graph those solutions anyways. So we'll just simplify this as far as we can. Now, 119. Its only factors are 7 and 17, neither of which are perfect squares. So there's not anything that we can pull out of this except just the negative. So we could think of negative 119 as negative 1 times 119. We're not going to do anything with the 119, but we know the square root of negative 1 is I. So I'm going to rewrite this as negative 5 plus or minus I radical 119. The 119 stays in. We didn't do anything with that. Over 6. And this is actually done. There's nothing else we can do to this. We could do the square root of 119 and get that decimal. It would be pretty close to 11, 10.9 or something like that. But it's not really going to help us. We can't graph that because we're not graphing imaginary numbers. So as far as we're concerned for now, that is the solution to this. And with the 6 down here, there's nothing really to simplify. 5's not divisible by 6, and we haven't pulled anything other than an I out of this. So this is our solution here. Sometimes when the solutions are complex, we actually end up with less arithmetic, which can kind of make it a little easier. All right, so for the last example, we're going to look at, this one has fractions. But we're not actually going to work with the fractions. We're going to work to get rid of these fractions so that we don't have to worry about working with them. And the way that we do that is to just multiply everything by the greatest common factor. So we're going to look at the divisors here. I'm sorry, not the divisors, well, I guess they are. But we're going to look at the dividends here and figure out what number we can multiply both of those fractions by to make the fractions go away, and that number is going to be the greatest common factor. In this case, it's 12. So if we do 12 times 1, that's 12, but then divided by the 3, that's 4. So this becomes 4x squared. If we do 12 times 1, that's 12, but then divided by the 4, that's 3. So this is plus 3x. 12 times the negative 2 is negative 24. And then what we do to one side, we have to do to the other. So 12 times 0 is just still 0. So now I'm not worried about this anymore. We have a new quadratic equation that does not involve fractions, so it will make plugging this into the quadratic formula much easier. So negative 3 plus or minus 3 squared, so that's 9, minus 4 times 4 times negative 24 over 2a is 4, so I'm just going to go ahead and say over 8. Alright, so as we continue this, again, we'll work inside of here first. So 4 times 4, or negative 4 times 4 times negative 24 is positive 384. And then we'll go ahead, and since it's positive 384, it'll be 9 plus 384. So I'll go ahead and add the 9, that's 393. So we now have negative 3 plus or minus the square root of 393 over 8. The square root of 393 is 19.8. So we have negative 3 plus or minus 19.8 over 8. We could go ahead and simplify this out and get our two different solutions here. Negative 3 plus 19.8 is 16.8 divided by 8 gives us 2.1. So there's one of our solutions. Now we'll find the other solution here. Negative 3 minus 19.8 is negative 22.8 divided by 8, negative 2.85. So there's our other solution. And again, the point of this problem was to see how we can deal with quadratic equations that have fractions, so that when we plug it into the quadratic formula, we don't have to directly deal with the fractions. We can kind of get rid of those in one step, create another equation that has the same solutions. So technically, if we graphed this equation and this equation, they would not look identical. There would be some things different about the equations, but their solutions would be the same. And since their solutions are the same, we can manipulate it in that way and find the solutions. So if we actually went to graph this equation, we wouldn't want to use some of the information from here other than just the solutions. But the solutions are the same, and that's what we're working on right now. That's what the quadratic formula gives us.